Yeah, let's continue. I like to talk about a lot about network stuff. If you did homework, you will find that the network getting more and more complex, and you're gonna need more time to train the networks. So in this lecture, maybe also this Thursday, we're gonna talk about more about how to make your program faster on your GPUs or using multiple GPUs. So that's unfortunately because the hardware is not so grow so fast. Even that NVIDIA managed to do 2 times speed up every year, but then the network itself maybe goes to 4 times speed up, 4 times more complex every year, and data set also increases. So it makes us pretty harder to try our best to get the performance from the hardware. Maybe after 10 years, the network is getting to stabilized and hardware still being fast, then we don't need to manage about all the things anymore. Okay, so the first topic is how to do a hybridized training to mix up all this imperative and symbolic programming. We talked about the imperative programming before. So far, we all use the imperative programming. So that is the common way to do in Python, in Java, in C++. So here is an example. Just 3 lines of code on the right. We first assign values to A and B, and then compute C equals to A plus B. So every time we execute every line, we actually run the code here. So it's pretty straightforward. It's easy to debug. If everything goes wrong, you just print the result, or using the breakpoint in your IDE, that's all. But if you did the homework before, you see that it has some issues here. Firstly, if you're using Python, there's something called a Python interpreter. Every time you run a line of code, the interpreter will first compile your code into a bytecode. Then this bytecode will run on the virtual machine for the Python. So every time the compilation and the runs on the virtual machine have overhead. So here we have 3 overheads because we issue 3 calls to the Python virtual machines. And also because it has interpreter, you need to run the code in Python, which means if the mobile phones don't have Python installed, then it's hard to run your Python code in your mobile phones. So the major issue for imperative programming is that the performance and the portability. On the other hand, we mentioned something called symbolic programming. If you use TensorFlow or Keras before, it's actually using symbolic programming. In this program model, we first define the program, and then we give data to execute. So in math, we do it that way. We first define the equations, and then feed with data to run. If we use SQL before, we first define a SQL synthesis, and then feed with data table to get the results. So here we give an example. We first write a string expression about C equals A plus B, and then we compile this expression to get executable objects, and then we give data A and B with values and evaluate. So the problem here is that, well, people don't like this way to program because it's pretty hard to use, and how to debug all this way, how to print. We're going to show real examples later how it's hard to debug all this code. But the benefit here is the speed. Because when you're going to compile this code, you know the whole program here. You can do a lot of optimizations because you know the whole program. For example, if I know that A and B are going to use after we finish the C, then we can just delete A and B to release the memory because GPU memory is so expensive. Similarly, if we have a very long program here and we actually to compute C, but in fact we didn't use C in any place, then we don't need to execute C equals A plus B. That's another optimization we can do. So, and the other thing is that because we can have the whole program first, and we compile once and run the code once. So it has a single core. No matter how long the program you have, I only do a single compilation and then run a single and call the function once. In addition, if you're using the symbolic way, we probably can present the program using a not so Python way. We can present by an intermediate presentation, And then it's maybe not so related to Python, and we can run the code without the Python, which means we maybe run the code in C++. Okay, so so far we see two programming things. One's easy to use, one's maybe faster. And in Ampersand, actually, we can get two things together. So far we see that how to define network by using n.sequential or n.block. And using the hybridized model, you're just using the hybrid sequential or n.hybrid block. Everything here is similar to before, only thing that we define the network dot equals to n.hybrid sequential, and we adding two dense layers as normal as before. The only thing here that if we call net.hybridize, we're going to switch from imperative execution mode to the symbolic execution mode. That's all. So let me give some concrete examples how to do the things.